Hi, this is Matthew Atkinson, along here with Sam Williams and Josh Spaeth, and today we're going to teach you a little bit about Forth. So, Forth is a stack-based programming language developed by Charles Moore. Its development has been incremental, but its origins date back to the year 1958, when Moore worked at the Smithsonian Astrophysical Observatory. His work there involved the tracking of satellites. However, it took about half an hour for his code, which was then on punch cards, to compile, and limited computer time meant he only got to run it about once per day. So, to help out with this, he wrote an interpreter that allowed him to compose the different equations of several satellites at a time. Through several different jobs through the 1960s, Moore gradually expanded his interpreter. Forth was largely completed by 1971 during Moore's work with the National Radio Astronomy Observatory. The first person outside of Moore to learn Forth was Elizabeth Rather. She went on to found Forth Inc. in 1973, which is still in operation today. There were no overarching objectives for the language, and throughout his career, Moore's guiding principle was to keep things simple. Moore simply wanted something that he found helpful to his personal productivity. Moore's moving from job to job and working with limited resources resulted in Forth being both portable and efficient. Forth is still in use today and is popular in astronomy, aerospace systems, and microcontrollers. Forth has been used to control scientific instruments on missions conducted by both NASA and the European Space Agency. Major missions include Rosetta, which is designed to study comets, along with deep impact, and instrumentation on the space shuttle before it was retired. Forth is a threaded, interpretive, stack-based language. It provides an interactive shell in which the user can define and run subroutines, which in Forth are known as words. It has no built-in type checking. All the type checking is up to the user. It is a statement-oriented, also known as an imperative language, and in addition, arithmetic operations are input using reverse Polish notation, also known as postfix notation. Forth is named for fourth generation software, not fourth generation hardware, as is often thought. The spelling is a result of a 5-character file name limit on the system he was using at the time, which I believe is IBM. Alright, so as a reminder, Pratt says data objects represent a container for data values, a place where data values may be stored and later retrieved. The stack is arguably the most important data object in Forth. The entire language is built around stacks and their manipulation. As seen here, the numbers 100 and 20 are placed on the top of the stack, or on the stack, with 20 being on the top. They are multiplied, and the result is placed on the top of the stack. The word, or in this case is a period, pops the top of the stack and displays it to standard output. Both the pound and the period are predefined words. In Forth, an entry is either defined as either a defined word, an undefined word, or an error. So here's an overview of some data objects, and we'll start off with the variable. The variable is a subroutine which returns the address of a memory location. The syntax is as shown. Storing a number in a variable is done as follows. The word, or in this case an exclamation point, sets the value attribute of the object to the number 150. The word, here the @ symbol, retrieves the value of the variable. Constant, which is obviously stores a value that cannot be changed, as demonstrated in the code segment here below. The words create a lot in here provide ways to set aside memory space and attach a name to it. Create makes a new dictionary entry. A code segment, the code segment above, creates a new entry named A. We can view the memory location as such, with a period. The here command will show the next available memory location. Here period shows the same as above, 20,000. So as you can see, the next available memory location is the same location that we named A. This is because we have not allocated the space, just attributed a name to it. To allocate cells, we can do the following. 10 cells allocate. This will allocate 10 cells, each of which are 4 bytes or 32 bits. These cells act as an array of size 10. Invoking the here command will demonstrate that 10 cells take up 40 bytes of memory. The syntax altogether for creating arrays, or an array of size 10, create a 10 cells allot, which creates an array labeled A of size 10. The index starts at 0, so storing a value into the array index 4 would be done as so. To retrieve the number, simply substitute the word, in this case an exclamation point, with the @ symbol. Value is a hybrid of variable and constant. Functionally, it is a variable since value can be changed. However, it shares a syntax with the word constant. The syntax is shown in the 3 bullet points below. The locals subroutine implements named memory locations that are local to the word definition. The memory is reclaimed after exiting the word. Syntax is shown as follows.
Hi, this is Sam Williams, and I have primitive operations, factoring, and sequence control, and I'll be talking about those today. Alright, so first off, primitive operations. As expected, there are arithmetic operations, as Matthew showed in his last, little 7 minutes. These include the addition operator, subtraction, division, multiply, modulus. There are floating point and hexadecimal arithmetic, and those are denoted by adding an e at the end, or doing f plus or f dot, which will, add floating point numbers, or f dot will give you the stack of the floating point number. So there are also stack manipulation, which is, some examples being drop, swap, rotate, duplicate, over, tuck, pick, and roll. Relational for, comparisons greater than, less than, equal to. To, which reassigns a literal to a variable. Matthew touched on this earlier. @ symbol, which fetches the address and puts its contents onto the top of the stack. Explanation point stores the value of the variable. A colon defines a word, such as the syntax below, colon, new word, and in parentheses is a comment. It basically tells you what the pre and post conditions are. If there's nothing before the 2 hyphens, then there's no preconditions. If there's something after the 2 hyphens as shown here, there's a post condition. So this new word will give us the value 5 as denoted in the syntax. And finally, the semicolon to terminate a definition. Here's an example of the stack manipulation operations. We feel that this is probably the most important set of operations because it is a stack-based language, and pretty much any arithmetic done on it, or anything, it deals with the stack, and so we have several of the stack manipulation operations listed here. If you'd like to go into more detail about this, feel free to pause the video at any time just to see the stationary version. On the next slide, we have a GIF format of constant, execution. So if at any point you wanted to stop the video here and see how the stack, handles drop, rotate, swap, and duplicate, you're free to do that as well. Moving over to over, tuck, pick, and roll. In pick and roll, you actually have to specify the number beforehand, and in this situation, 3 pick would be, picking the top 3. So, which is denoted in the next area here. We have 3 more GIFs that you can pause at any time and see, what these exactly do. Moving on to factoring. The current trend in Forth is to avoid making the stack deeper than 3 or 4 elements. If a word is making it deeper, then it should be factored into another word. This is just common, programming experience from everyone to not make things as complicated as we can. because if a stack's going 10 or 12 lines or 10 or 12 elements deep, it starts getting really complicated, and in every programming language we're trying to avoid that. So factoring is the process of breaking out these repeated pieces of code from subroutines and giving them a name. This will shorten the overall program as well as make the code simpler to read. Factoring well usually makes the code read like an English sentence. For example, a robot control program might be factored to read 2 times left eye wink, which is completely understanding to us. Here's an example of factoring using washing machine functions. At the very bottom level, or top level, which is at the bottom, it says washer, which does wash, spin, rinse, spin, which everyone can understand. That's what a washer does. But if you want to go into even more detail, you can go back up into the top parts and see what wash does, see what rinse does, see what spin does. So, this is an explanation of the syntax on the previous slide. The top level controls calls off to the other subroutine defined above, which call off to even more subroutines. This makes it easy for the programmer to read, better debug, and add additional functionality. This goes back to the fourth program's reading like English to aid the programmer. Sequence control. Recursion, through the use of the word recurse, is one of the forms of sequence control that we have. A note on recursion. Forth adds virtually no access overhead in recursive calls because it uses the stack directly. Because of this, if recursion is the best way to program the algorithm, there's no reason not to use it. I gave some syntax here to show how recurse is used. Feel free to read over that. The next section for sequence control is indefinite loops, which also known as while loops. Here's the syntax for that. And lastly is the definite loops, which are permitted only within definitions. You cannot use them in the interactive environment. These are known as iterative loops or for loops if we're talking about most programming languages. The syntax below. The general form of sequence control is denoted by this picture. Forth only checks for 2 types of data when input is given, a word or a number. If an input is not a word in the dictionary, it will attempt to convert it to a number. If this conversion does not work, then an error message is issued. We believe that this picture is probably one of the most important aspects of Forth because it's so simplistic. Charles Moore values simplicity. He wanted it to be an easy language for people to pick up and still be efficient. So the fact that this picture is easy to read and everyone kind of understands it, it makes Forth very simple. Sequence control during compilation. When defining new words to add to the dictionary, Forth must change from interpret mode to compile mode. Because of this, a new graph explains what actions are performed during compilation. As just stated, there's 2 different types of modes in Forth language. There's a compile mode and an interpret mode. The last slide gave you the sequence control in interpret mode. This slide gives you the sequence control in compile mode. So, brief going through here. It sees if it's a word. If it is already a word that's an immediate word, then it goes ahead and executes it. But if it's not, meaning it hasn't been defined before, it goes ahead and tries to compile it. If it's not a word, it goes back to being, okay, is it a number? And then if it is, then it goes ahead and just stores the value of that number. If it's not, then it boards with an error.
This is Josh Spaeth. I will be discussing data access, storage management, and operating environment aspects of the Forth programming language. For data access, there are 2 of the most important commands in Forth for data creation and access, and they are called create and allot. These 2 commands are used for storing memory in the language. Create is the command that someone would use to create a new variable in Forth, and allot creates memory for that variable on the disk. Because the 2 words create and allot are existing in Forth, Forth does not use data structures because create and allot make those data structures themselves. After data has been stored into the memory, primitive operations that are built into the language allow for retrieval of that memory. The @ symbol, for example, fetches the address of specific memory. That way it can be looked at and see where that specific variable is. And the exclamation point symbol allows one to store a value into a variable. For storage management, Forth is mainly a stack-based programming language, and all of its storage management is used through stacks. Forth utilizes two types of stacks in its implementation. The most important stack of all is often called the parameter stack or the stack. The next stack is called the linkage stack or the return stack. Words created in Forth operate at the top of the parameter stack, so this means that when the words are being ran on the compiler or the interpreter, they are coming from the top of the parameter stack when they are used. When they go out of scope, they are removed and they are put onto the linkage stack. And then the return addresses for the words are stored on the second stack or the return stack. As with many programming languages, Forth has operations that modify the stack. These are some of the operations for the stacks in Forth. Sam has already referenced some of those. Data from the two stacks can be moved to and from the stacks using these operations shown below. These operations are very important for moving to and from the main stack and the return stack because it allows the user to be able to specify where they want all the words to go. For the operating environment, Forth uses port access words to make portability easier. Now, portability is made easier for devices in which the input-output space is separate from the CPU. Some of the port access words include those shown below. Now, the C, W, and L in these port access words refer to 8, 16, and 32-bit memory access. The P at and the P exclamation point refer to native cells in the Forth programming language. In file handling for Forth, Forth uses three data types for file handling. FAM is the file access method, IOR is the input-output result, and file ID is the file identifier. When file handling, these operations can be used on specific data types. The BIN data type, it modifies the FAM file handling data type to include binary. So this kind of means your file access method is going to be able to use binary. The RO operation, it will change the FAM data type to allow you to change it to read only. The WO turns the file access method to write only, and the RW turns it to read and write. You can also create files with the create file function. It will create a file on the hard drive, and it will return a 0 if the file was successfully created and filed. Open file will open an existing file, and close file will close it. To write memory to an existing file, you would use the command write file. While Forth is known as a threaded interpreted language, this is a common misnomer because a threaded interpreter is an implementation detail, not a characteristic of the language. Forth is usually implemented using a threaded interpreter, which leads to this misnaming of Forth. That being said, we will continue to call Forth a threaded interpreted language for simplicity's sake. Now, a threaded interpreted language is a language that can interpret commands, subroutines or programs, typed in at the console, as well as create, compile new subroutines and programs. Forth is considered a threaded interpreted language because when executing words from the dictionary and putting numbers on the stack, it is in interpret mode. When defining a new word for the dictionary, Forth changes to compile mode. Forth allows immediate debugging and executing new subroutine calls while still maintaining efficient execution for an interpreted language. Now, Thank you to Matthew for allowing us to have a way for installing Forth. Our implementation of Forth is called gforth. A script to install gforth on a Linux system can be found at the following link. Copy and paste the code into a file and then execute the following command. Log out of your shell and then log back in. Typing gforth will open the Forth environment. These are some of our references that we've used to find some of the information presented in this presentation. If you have any questions, please refer back to some of these information-rich websites for Forth. This has been our presentation for the Forth programming language. Thank you for your time.